Okay, so in the last topic, we looked at rate of reactions. That was the first part of managing chemical processes. And in this subtopic, we're going to look at equilibrium and yield. So the rate of reaction is really about how fast or how slow a reaction happens, so how fast or slow we make the products of a reaction. The equilibrium and yield looks at how much products we get with respect to the reactants. And what controls how fast it happens, as opposed to the theoretical how much product you can make, are controlled by slightly different factors. So the two things are related, but we also need to consider them quite separately. So in part A, we are going to look at equilibrium constants, exactly what they mean and how we use them. Let's get into it. So a couple of definitions to start. An open system is one that can exchange matter with surroundings. For example, if we react calcium carbonate and marble chips with an acid, that will release carbon dioxide. Carbon dioxide will be lost to the surroundings. So we would consider that an open system. A closed system is one that cannot exchange matter with the surrounding. So if you like, it's a sealed type environment. Probably the most common one we will use here is where we're doing a reaction of two things that are dissolved in water. Those two things can't generally escape from the water, so we could regard that for all intensive purposes as a closed system. Now in the previous topic we looked at diagrams like this where we had some reaction, let me just write here, of some reactant going to form some product, and we looked at over time the reactants will decrease until they eventually reach this flat line. As we use up the reactants we will form products, so that will increase, and if we wanted to work out the rate we would find the slope of this line at any point. Now we saw these lines sort of flattening off to horizontal or a zero slope, but we didn't talk much about that. But that basically means we have reached equilibrium. So the concentration of the products is not changing. The concentration is constant, the slope is zero, the rate is zero. Same here, the concentration of the reactants is not changing. Now, really important point here. This doesn't mean the reaction has stopped, okay? So I might even write that here. It doesn't mean the reaction has stopped. So that would be wrong, because what's actually happening is we have what's called a dynamic equilibrium. And all that means is the rate of the forward reaction, i.e. the rate that we are making products, is equal to the rate of the reverse reaction. That is, that products are being turned back into reactants. And for that reason, we don't usually write an arrow like that, so I'm going to scrub that arrow out. We usually write an arrow, and I'll do it in red, that won't matter, like this, particularly when we're talking about equilibrium. Because yeah, reactants can go to form products, but we can also have some of the products being turned back into reactants. And what's happening in this zone here is the forward and the reverse reaction are happening at the same rate. So there's no net change in the concentration of the reactants or products. So the way we usually describe these relative concentrations once we've reached equilibrium, so the amount of reactant to product, is using an equilibrium constant. Talk more about what this means in the next slide, but just to introduce how that we write those. If we've got some hypothetical reaction where A moles of A plus, or A molecules of A plus B molecules of B goes to C molecules of C plus D molecules of D, etc. The equilibrium constant, Kc for that reaction, we would write the concentration of C. So remember, square brackets means concentration. So square brackets means concentration. We've talked about that before. So the concentration of C to the power C, so we start with our products on top. So products are on top. times by the concentration of D to the power D over the concentration of the reactant A to the power A times by the concentration of B to the power B. Bit confusing, so let's look at a real example. If we have sulfuric acid, reacting with two sodium hydroxides to form sodium sulfate and water, how would we write the equilibrium constant for this reaction? The concentration of sodium sulfate, which is product here C, if you like, from here, times by the concentration of water. Now, there's a 2 in front of that, so we put a 2 up there. Theoretically, we put a 1 up here as well for sodium sulfate, but anything to the power 1 is itself, so we can ignore that. Divided by the concentration of sulfuric acid times by the concentration of sodium hydroxide, but that's squared because there's a 2 in front there. So that is how we write an equilibrium constant. Let's explore equilibrium constants a little bit more in the next slide. Okay, so to demonstrate equilibrium constants, I'm going to use a concept that you've probably already, or hopefully already heard of, and that's talking about strong acids and weak acids. So we would have said previously in year 11, strong acids completely ionise. So that means when you put something like nitric acid, which is a fairly strong acid, into water, it all breaks apart into the hydrogen ions and the nitrate ions. So it releases lots and lots of hydrogen ions, which is what makes something acidic. So that's a strong acid. Acetic acid here, CH3COOH, is a weak acid. And we would have just said that partly ionises. What that means is when you put acetic acid into water, most of it stays as acetic acid, and only a small part of it ionises to form the acetate ion and hydrogen ions, so releasing these hydrogen ions to do the acid thing, so to speak. So we can actually describe how much this ionises using an equilibrium constant. So the equilibrium constant for this reaction at standard temperature and all that sort of stuff is 240, whereas for this one here it is only 1.8 times 10 to the minus 5. So this is a really small number, like 0.0000185, something like that. So much smaller equilibrium constant for the partially ionisers, much larger for the completely ionisers. So let's do some sort of calculations with that. Let's say the concentration of acetic, we have a solution and we know that the concentration of H plus ions here is 2 moles per litre. Now if we know we've got 2 moles per litre of this, for every one of these that forms, we'd also get one nitrate form, so the concentration of nitrate would also be 2.0 moles per litre. So if we wanted to work out how much of that was left as nitric acid with the hydrogen still attached, so not ionised, we can use this equilibrium expression, which is Kc equals the concentration of H plus, the product, times by nitrate, the other product, divided by HNO3, the reactant. And we get that Kc, hang on a sec, we know what Kc equals, don't need to write Kc again. So Kc is equal to 240 up here, equals 2.0 times 2.0 divided by the concentration of nitric acid. We need to do a little bit of algebra there to solve that. So we want to, get rid of the HNO3 on that side. So I'm going to times both sides by the concentration of HNO3. Running out a bit of room. So that cancels. Then I want to get rid of the 240 there. So I'm going to divide both sides by 240. And we get left with the concentration of HNO3 equals 2 times 2 is 4 divided by 240, which is equal to 0.017 moles per litre. So you can see here a very small amount of it left as HNO3, a very large amount of it, 2 and 2, has been converted to H plus and nitrate ions. So we would say that reaction has gone to almost all products, so it's favoured the formation of products, or we might say, we often talk about this equilibrium shifted to the right, so it favours the product side on the right as opposed to the reactants on the left. And that's basically our equilibrium constant is giving us a measure of the relative amount of products versus the relative amount of reactants. So now let's look at the weak acid, and I've just made a quick correction here. I had put the concentration of hydrogen ions, but I want the concentration of acetic acid. I hadn't used that before, so that shouldn't matter. So let's look at, for the weak acid, working out if we had put 1 mole per litre of acetic acid into solution, how many hydrogen ions would be released? And rather than just say only a few because it partially ionises, we can now use this equilibrium constant here to calculate that. So firstly, let's just, to make the maths a bit easy, realise that for every acetate ion that forms when acetic acid releases a hydrogen, we will also form 1 hydrogen ion. So they will be equal, and I'm just going to call them X to make the maths a bit easier. So that means our equilibrium constant now becomes 1.8 times 10 to the minus 5, which is the equilibrium constant, equals X times X, and we should know that X times X is equal to X squared, divided by the concentration of acetic acid, which is given in the question, which is 1.0 mole per litre. Now the algebra is pretty simple here because x squared divided by 1 is equal to x squared. We don't even really need to rearrange. So we can go that x squared equals 1.8 times 10 to the minus 5. Therefore x is equal to 4.2 times 10 to the minus 3 moles per litre, so quite a small number, and that is obviously equal to the concentration of hydrogen ions, which is the sort of thing we were most interested in, and as I said before, that's also equal to the concentration of acetate ions. Now, often in these questions you get asked to fill in one of these boxes to look at what happens during the reaction to the amount of products and reactants. So we've just worked out here, let's say at equilibrium we have got I might just change pen colour for this one. Oops, that's not a pen, that's a highlighter. We've got 1.0 moles of acetic acid, and we've got 4.2 times 10 to the minus 3, and I'm going to write that out in non-scientific just to make this one a bit more obvious. 4.2, and that's going to be equal to the concentration of the acetate ion. And let's say the question tells you that initially when you started this experiment you had no hydrogen ions and no acetate ions. So you were basically just adding pure acetic acid to the water. And it wants you to work out, well, how much acetic acid must have been there originally. So, if you like, the change in the hydrogen ion concentration has been plus 0.0042, because that's gone from 0 to 0.0042 for both of them. Now, so how much must have the acetic acid concentration changed? Well, if you look back at our reaction, for every one acetate or one hydrochloric, so one acetate or one hydrogen ion that forms, we must have lost one acetic acid molecule. So that one has changed. If you like, we've lost 0.0042 of our reactant. So that means initially there must have been 1.0042 moles per litre of acetic acid. And then we lost that amount that was converted to the other things. So this one's dealing with quite small differences, but you will typically see these tables in equilibrium questions. That's it for equilibrium constants. In the next video, we will look at Le Chatelier's principle. Cheers.